Hi, everyone. Welcome. Today, I'm going to be discussing recent results from the ISOIS investigation, the Integrated Science Investigation of the Sun, on the Parker Solar Probe mission. Through Solar Probe, we are discovering the energetic particle environment near the Sun. I'd like to acknowledge my collaborators and those who have made the Parker Solar Probe mission possible. Okay, so here's the abstract. I won't read every word, but today I'm going to be talking about energetic particles from close to the Sun, basically results of Parker Solar Probe's first 5 or 6 orbits, and the discoveries of how energetic particles begin to be accelerated from very close to the Sun. ISOIS is the energetic particle suite, measurement suite on Parker Solar Probe. We measure particles from about 10 keV up to hundreds of MeV per nucleon, gradual, impulsive solar energetic particle events, energy spectra composition, timing, pitch angle distributions. We measure helium-3 as an indicator of impulsive events, as well as other populations, co-rotating interaction regions, ACRs, anomalous cosmic rays, and galactic cosmic rays from outside the solar system. These all provide complementary information on particles' radial dependencies, as well as their behavior and interaction with events produced by the Sun. In addition to ions, we also measure electrons from about 0.025 to 6 MeV, and I'll show you some of those measurements as well today. These show the 2 instruments covered by ISOIS, epi-low on the top, epi-high on the bottom right. You can see pictures to the right of epi-low and epi-high, the lower energy and the higher energy instrument. You can see with epi-low the mini apertures that allow us to get very detailed information on the pitch angle distributions of these energetic particles. And there's ISOIS sitting near the back of the spacecraft on the RAM side of the spacecraft on Parker Solar Probe, which goes very, very close to the Sun, and will continue to over the coming years. One thing we've emphasized is that the tools for analyzing the data, for plotting the data, are all available from the Princeton website, and are also available via SPDF. We have now released data through August 13th of 2020 and continue to make data releases. And we encourage you to get out there and use the data and let us know about your studies so that we can participate. Where are we now? So Parker Solar Probe has gone very close to the Sun inside of 0.2 AU in its first orbit of the Sun, first perihelion. It subsequently continued to go close to the Sun up to orbit 3, orbit 4 and 5 and 6. We just finished orbit 6 near the end of the year of 2020. We were at apogee, and currently we're going in towards the 7th perihelion. This is where we are now as of January 6, 2021. These are the actual orbit. You can see that we're almost about to plunge close to the Sun. By January 20th, we will have moved through our orbit 7 perihelion. You can also, you see this on the left in the standard inertial reference frame. On the right, we see this in heliographic coordinates. You can see this, what happens in each orbit. This is a particularly beautiful example where we co-rotate with the Sun and then actually move backwards. So at this point, near the 20th, we will be sampling regions connected in the solar reference frame over a relatively small range of longitude and latitude that gives us an opportunity to really study on very particular regions on the Sun. This shows the first 2 orbits. On the inside of these plots, we show data from epi-low, the count rates from epi-low. On the outside, the count rates from epi-high. you can see very clearly the various events. As we will see, the first few orbits have been very quiet orbits. The energetic particle events are very, very low. So you will see a series of co-rotating interaction regions. This is orbit 1. Event A and B are both co-rotating interaction regions. We see this event here, which was a CME-SEP event, followed by an interaction region. And you can also see seed populations from relatively close to the sun, and even this curious event that happened very near perihelion. We're lucky to see this. These are all extremely small events. In orbit 2, we saw I view this as a double SEP event. You see the low energy particles first, and then the higher energy particles. These are actually separate events with different characteristics, homologous events erupting from similar interaction regions. SEP event here, SEP event here. This was, to this point in April of 2019, the largest SEP event observed. And we also see stream interaction regions, stream interaction region here, solar energetic particle event, and so on and so forth. This is an example of the orbit 1 CIR event. So in particular, if you plot the event as a function of the foot point solar longitude, these are events that are separated by basically 2 rotations, almost 60 days. And you can see still the character of the event remains almost unchanged. Co-rotating interaction regions form basically a steady state in the co-rotating frame. So when you plot them as a function of solar longitude, you see very, very similar behavior. This is just a stream interaction region producing energetic particles, accelerating energetic particles further out from the sun that stream back into the observer at Parker Solar Probe, very close to the sun. This is the second event that I mentioned in orbit 1. This is kind of a remarkable event because you see all the characteristics of both the CME and an interaction region. So you see the development of a CME near day 316 of 2018. You see the passage of the CME right here. You also see a dispersive event that happens early on that's basically produced by flare particles as the event is being ejected close to the sun. And then you see in red here, a stream interaction region of a fast wind overtaking slower wind. And then you actually see just the beginning of particle acceleration when the compression region goes by. So you see in this one event, both the CME, the SEPs, dispersion, as well as the co-rotating interaction region. And you even see then later in the event, the CIR particles that are streaming back to you from out in the heliosphere. So that is as the CIR becomes more developed, you're seeing particles connected to the interaction region further out in the heliosphere. Beautiful event. It summarizes a lot of the types of characteristics that we see in solar energetic particles. This is one of the SEP events that occurred in the second encounter, very near perihelion. You see first, early on in the event, this is between day 92 and 93 of 2019, a dispersion event, relatively low energies, very little in the high energies. And then the second event, you see mostly the high energy particles, very little of the low energy particles. We actually know that this was a Z-rich event and that it was, produced by eruptions of loops and coronal structures very close to the sun. You see type 3 radio bursts associated with the event. And you can see the evolution of the event from day 92 to 96 in the various energy intervals. And you can see the second event, higher energy event, very different in character from the lower energy event. And when we say high energy, these are actually very low energy particles. So even though these events are very, very small, we still see enormous variability. This is a homologous eruption, an eruption from close to the sun that keeps pulsing out energetic particles. This is an event that happened later in orbit 2. This is in April of 2019. You can see these gray regions are actually X-band passes where we cannot get the data down. We lost data due to the X-band passes. but we are still able to see the background of the event coming by. You see, you know, a CME, a number of CMEs that take off. The ICME, the passage of the compression region, happens right here near between day 111 and 112 of 2019. That was between April 20th and 21st. And interestingly, when that CME went by, we saw the compression region in the material in front of the CME, and you actually see the seed particles and the energetic particles from the event are essentially compressed by the plasma in front of it. And this process of compression and acceleration is actually an important step in the acceleration process, because it takes seed populations and enhances those seed populations for further acceleration further out. Another characteristic of this event, which was shown in the Weidenbach et al. APJ study of 2020, is that it was a helium-3 rich event. So we know that those particles which were being compressed and swept up in the CME, in front of the CME, were actually filled with energetic particles coming from solar flares. And we saw SDO AIA jets, GOES solar X-rays, and type 3 radio bursts, all showing the flaring that was happening associated with the event. Subsequently, you see both helium-3 and helium-4 out at Parker Solar Probe. And we also see helium-3 and helium-4 out at ISOIS for this event. So we're really able to pull together these different diagnostics and show the combination of flaring and compression of those seed particles, which makes up the event. Okay, so that was the events that happened in orbit 1 and orbit 2, going from 2018 through early of 2019. We also saw events throughout from mid to late 2019, early 2020. That's orbit 4, mid 2020, orbit 5, and late 2020 for orbit 6. Now, interestingly, you will see that you see one SEP event, orbit 1, 3 SEP events in orbit 2. I've circled them all here. We had no events in orbit 3, 2 events in orbit 4, 3 in orbit 5, and there's actually more than 3 that have occurred in total in orbit 6. These SEP events are all associated with eruptions, flaring, and coronal mass ejections, activity from the sun, but they're all extremely small events. With the timing, it doesn't seem to make too much sense, but then when you take a look at what's happening in galactic cosmic rays and in the sunspot number, you realize what's going on. We started in orbit 1 during the decline of solar activity, get to a minimum exactly in orbit 3. This is where we saw no SEP events, and then the rise in activity in orbit 6. And now we're going to see additional increases in solar activity as we head towards solar maximum. So in a way, we are at a separator where we've seen very, very small events from Parker Solar Probe that we've been able to piece together. And at this point, we're going to see much more complex events, much larger events associated with a more active sun. On the right-hand side, I show data from the Cosmic Ray Telescope for the effects of radiation. You can see the blue period here is this solar minimum period that we see, and we actually see galactic cosmic ray fluxes that are higher than what we saw in the previous solar minimum, which we know was one of the deepest solar minima of the space age. So we're actually seeing even deeper solar minima that we saw previously. This is indicative of a sun that has gotten very, very quiet, the quietest that we've seen in the space age. Okay, additional events. This was we have observed the passage of a coronal mass ejection at around 0.3 AU. This was summarized in a Joyce et al. Study. This particular event was a relatively small event. We saw erupting loops that gave rise to the coronal mass ejection. And then during the passage of the actual CME, you can see that you first saw the heliospheric current sheet crossing. This was in very early in January of 2020. day 20 through 22, roughly. You have the CME arrival just before day 21, and the CME departure during day 21. So relatively small structure that was going by. You do see energetic particle enhancements, but interestingly, when you look at the actual anisotropies in these are particles coming from the sun, and you can see that there's a period where you essentially have a beam of particles that are coming backwards towards the sun. This tells you that you're actually embedded internal to the coronal mass ejection, seeing particles that are accelerated out toward the front of the CME and beaming in towards the sun. This gives you a much more structured acceleration than we've ever been able to see, because we're seeing the acceleration process right at its as it begins. Another example, this was a study that was written up by Cohen et al. In the ANA special issue. This is a series of eruptions of 5 different events, actually 6 different events that we're seeing. These again are homologous eruptions, relatively small flares that just keep coming out from the same active region. In the Cohen et al. Study, we were able to study the helium to hydrogen abundance. We saw huge variations from 0.003 up to 0.18 in helium to hydrogen ratio. That is at 2 orders of magnitude variation from the same homologous erupting active region. This just tells you we're just seeing that variability in energetic particles right from its source, and this resolves a pretty significant question about what causes the variability. You can see that an individual source is indeed that variable. And lastly, I'd like to point out some of the electron events that we've started to study. This is being worked on in a paper that's just been published by Mitchell et al. in this year. And in particular, you can see electron events and how they're correlated with type 3 radio bursts. This is data that we're just starting to really dig into and understand the backgrounds fully. So it's a pretty significant achievement that we can dig out these events. These are probably the smallest electron, or they are the smallest electron events that have ever been studied close to the sun. Events this small do not persist out to 1 astronomical unit. So it's only from being able to get close to these events where you're able to see these small eruptions. And again, this addresses a question as to why for type 3 radio bursts you don't always see electron sources. And the answer is because the events themselves can be relatively small and be lost before they get to 1 AU and beyond. So I will conclude there. We have seen during this first phase of the Parker Solar Probe mission, as we've gone close to the sun, the first 6 orbits, we've been seeing the sun and the solar wind in a state very, very close to solar minimum. We were able to see very much smaller energetic particle events and piece those apart in ways that we've never been able to see before because we've gotten so close to the sun. We see helium to hydrogen variations by almost 2 orders of magnitude in 6 homologous events, eruptions from the same active region. Helium-3 enhancements in relatively small seed populations. So these are very small events, but nonetheless, we're able to piece together the seed populations produced from flare eruptions and then compressed in the fronts of CIR. So we're able to piece that event together in great detail. Association of small electron events with type 3 radio bursts. These are events that are not able to be seen further out in the heliosphere. And we see one instance of the inward streaming of a remote acceleration site during the passage of a CME, showing particle acceleration at very early stages where the acceleration process is not at all uniform. It's in fact coming from relatively localized sites out in the CME. We also see a Z-rich event, which is interesting that we are able to see a Z-rich event in such small solar energetic particle events. As I've already said, these events all straddle solar minimum, and really what we're seeing here is that there is no one single acceleration process that can explain all the events that we've seen. The variability is caused by a combination of essentially all the above. solar flares that are coming from close to the sun, acceleration through magnetic reconnection, acceleration through stochastic processes, acceleration through compression, and acceleration through shock acceleration. And I'll end there. Thank you very much.